Hi everyone, and welcome to another seminar of mathematics and high energy physics. Today we have the fifth lecture in supersymmetry. The Professor Silvia Penati, please go ahead.
Thank you. Hi, everybody. Okay, so as announced already last time at the end of the previous lectures, the subject of the today lecture will be superspace. Superspace is a very convenient tool to organize in a very compact way representations of the supersymmetry algebra, and beyond that, it's a very, at least in 4 dimensions, in n=1 supersymmetry 4 dimensions, it is a very, very convenient mathematical tool where we can do quantum calculations, perturbative calculations very efficiently. But as we already discussed last time, before going through the construction of n=1 superspace, actually I should write maybe in order to be more explicit, n=1. This is something that I want always to stress. What I'm going to do here is really true only for n=1 supersymmetry in 4 dimensions. If you change dimension and you change the degree of supersymmetry, things change, okay? So n=1 superspace, as I said before going through the construction of n=1 superspace, I have to review the construction of ordinary Minkowski space as a coset. Let me just write down a few equations that we wrote already last time. Remember that last time we discussed how Minkowski space-time can be identified with the coset Poincaré group, coset Lorentz group, or if you wish, in a more mathematical language, ISO 13, coset SO13. Remember, the coset is a set of equivalence classes where G and G prime group elements, this is the generic group, belong to the same equivalence class if and only if G prime differs from G by a Lorentz transformation. Let's say, in this case, SO13. Okay, and this is nothing but what I write here with this dot is nothing but the composition law of the group. Okay, as we saw already, we can then describe or identify each equivalence class with a representative. So we pick up one representative per class. And the choice that we make is the following. The representative is of the form e to the I x mu p mu. P mu are the translation generators. And as far as I consider in the group, x mu are simply 4 parameters, real parameters. So 4 real parameters. But as we discussed already last time, the nice thing is that these 4 real parameters can be identified with coordinates of points in the in the Minkowski spacetime. These are identified with the Minkowski coordinates. Okay, Therefore, up to Lorentz transformation, there is a one-to-one map between group elements, elements of the Poincare group and points in Minkowski spacetime. This is why we claim that Minkowski spacetime can be written as a coset. Okay, now let's work out a little bit of algebra about, Poincare group and Minkowski, doing this sort of parallelism between Poincare group and Minkowski spacetime. Of course, if this is first of all, if this is the representative of a given class, the class will be, as I said, identified by this set of x coordinates, x parameters. Any other element, group element, in the same class is of the form g of x equal to the representative composed a Lorentz transformation by definition of equivalence class and by definition of coset. Okay, of course, if we consider the group composition law written in this language, is the following. If you compose G, let's take a generic G in the Poincare group with the representative of a given class, L of x, you will obtain L of x prime composed H, in the sense that if you compose a group element G belonging to a given class with the representative of another class, you will end up into a third class, which can be identified by coordinates x prime up to a Lorentz transformation, because this is the generic form of an element in the class x prime. Okay, I will exploit this composition law to show you a few nice things that happen. Okay, so let me go through two very relevant examples of composition law. Consider two relevant examples. Let me give it a name to this equation of composition 1. Okay, let me consider first composing two, let me take G of x to be exactly the representative of class x, and let me take a second G, let me call it G of psi, still given by the representative of another class parameterized by psi. And I want to consider the composition of G of psi composed with G of x. Okay, as I said, this will be, according to the composition law 1, some representative L of x prime compose a possible Lorentz transformation. So I want to understand which is the explicit expression for this new representative L of x prime and this Lorentz transformation H when G are chosen this way. This is what I'm going to do. Okay, so let's look at the left-hand side of this identity, and let's work out the composition using the fact that we know which is the explicit expression for these representatives. The representatives, remember, are written in this way. Therefore, if I compose now G of psi compose G of x, which is by definition, look at the way I choose G, this is nothing but L of psi compose L of x. This is equal to e to the I psi mu p mu composed e to the I x nu p nu. Okay, however, remember that when you deal with the exponentials of operators, you have to pay attention what you do. However, you know, P and with P commute, so these are like numbers, therefore you can simply rewrite this, the product of two exponentials as a single exponential given by e to the I psi plus x mu, P mu. I hope you agree with me. Okay, and of course, this is by definition of the form L of x prime compose H, where x prime mu is exactly x mu plus psi mu, and in this case, H is equal to 1, the identity operator. Okay, so what I find, and this is another important piece of the story, is this transformation. So when I take for the two G elements, G representatives, basically the composition law, a group of two group elements, translates into a transformation law for the x mu parameters, which are nothing but the Minkowski coordinates. Okay, in this case in particular, I find that the composition law corresponds to a translation in Minkowski. Okay, this is nothing but translation. Where do I write it? Here, translation in Minkowski. No way. Let's try this. Translation in Minkowski. Okay. We will see another example, but I want to stress already at this level that hopefully you understand how, you know, I can translate composition law into something which looks like a transformation in Minkowski. Another piece of story still concerning this kind of transformations goes as follows. We can claim basically that in terms of fields, we can realize the representations of the Poincare group. Okay, so representations of Poincare can be realized as in terms of smooth functions of x mu. Let me call them phi x. Okay, which belong to some representation of the Lorentz group, and we will come back to this point a little bit later. Let me now focus on phi of x, forget about Lorentz for the time being, and satisfy the locality constraint. This is also important. The locality constraint is the following. If you work in a frame where, you know, the coordinates is x, when you move to another frame with coordinates x prime, you will have that, you know, your function phi will change sort of functional form. So we can call it phi prime, but the locality condition requires that these two quantities have to be the same. Okay, this is, you know, basically the first and main assumption at the basis of quantum field theory. In fact, you know, this is why quantum field theory is a local field, a local theory. Okay, what can we now infer from this locality constraint. Let me give it, what's the name? Equation number 3. Okay, if we are looking at translations, so x prime is expressed as x plus psi, this can be written under translations. We can rewrite this constraint as phi prime of x plus psi equal to phi of x, or, sorry, let me move it a little bit here, or equivalently, phi prime of x equal to phi of x minus psi. Very good. We define the action of translation operator on the fields as, so this is a general definition, phi of x plus y equal to e to the I y mu p mu, phi of x e to the minus I y mu p mu. Okay, this is definition on how we define translation in general for fields where p mu are, as usual, the translation generators. So this is nothing but, this is equivalent to say that phi of x plus y is the representative of my coset Ly, phi of x, inverse of the representative. Good. Now, let's work out how p mu indeed acts on phi, considering the locality constraint written in this way. You know, here we have 3 equivalent ways to write the locality constraint. Let me consider this one. Okay. Therefore, what I do is to look for, so we look for the functional variation of phi under translation, defined in this way. So like the functional, let me call delta 0 of phi under I would better say let's stick to infinitesimal translations. Okay. Infinitesimal translation means that I'm going to consider this psi, when I write psi here, a very small number, very small quantity. Okay, so the functional transformation of the field phi under infinitesimal translation is, first of all, by definition, phi prime of x minus phi of x, okay, which is different from this, what I write here. If you consider the complete transformation would be phi prime of x prime minus phi of x, which is 0 by definition. What I'm going to consider here instead is phi prime and phi evaluated at the same point, which means that I'm really looking at the functional variation, how the function phi varies under translation. So this is for what I wrote above. You know, if I now use that phi prime of x is phi of x minus psi, this is nothing but phi of x minus psi minus phi of x. Okay, but if psi is infinitesimal, you can, you know, perform the usual Taylor expansion. This is phi of x. If you expand at the first order in psi, this is phi of x minus psi mu d mu phi of x. Then you will have order psi square terms that I'm going to neglect, minus phi of x. Of course, these two terms cancel. And what you obtain is that delta, the functional variation of phi is minus psi mu d mu phi of x. This is something that we put in our pocket, okay, keep it there. Now, consider the general definition that we give here for translation acting on fields, okay? Therefore, what I can do is to rewrite, let me go here, this phi of x minus psi here. So I will start again from this expression, substituting, replacing phi of x minus psi here with the definition that I read here from the general definition of translation. Okay, so let's go back. Let's say, this is one thing. So on the other hand, we can alternatively write that delta 0 of phi, I'm just computing the same thing, which is phi of x minus psi minus phi of x, okay, now can be computed using another, let's say another procedure, which means I express phi of x minus psi according to my definition of translation. Okay, maybe I should give this another name, 4. So here I'm using 4 minus phi of x. Good, but since psi is infinitesimal, I can expand this expression at first order in psi. So if you allow me to go a bit faster, this will be minus I psi mu p mu applied to phi of x plus, of course, order psi square that I'm going to neglect minus phi of x. Okay, again, these two terms cancel. And now if I compare, here I was computing basically the same thing. In one way of doing the calculation, I ended up with this result. In a second way of doing the things, I ended up with this result. Therefore, the two results have to be, of course, the same. Okay, fortunately, they are both linear in psi mu. Well, this is the way I did things. So you immediately realize that comparing 5 and 6, with 6, we obtain that the action of p mu on my local field phi is nothing but minus I d mu phi x. And this is something quite important that we will exploit when we then go to the construction of the superspace. So let me give it another number here. Okay, good. Now, if you don't mind, I will go through the second example in a little bit more, a little faster. Remember, I told you that I was going to study the group composition law in terms of transformations in Minkowski space-time, considering two relevant examples. The first relevant example is what I have done now, concerns translations in Minkowski. The second relevant example concerns rotations in Minkowski, okay? So in the second example, what I would like to do is to consider, you know, remember the group, remember the composition law that I wrote above. G composed L of X equal to L of X prime composed H, okay? Now, we take G to be e to the I over 2 lambda mu nu n mu nu, where n mu nu is a Lorentz generator. Okay, therefore G is, of course, an element of Poincare group, but in particular, it belongs to Lorentz. Okay, I'm free to choose this particular G. L of X will be still my representative that I wrote above. And now you have to compose these two elements. This is something that I can ask you to do as an exercise. Okay, so if you compose these two elements, you will get into the I over 2 lambda mu nu and mu nu composed with e to the I x, let me call this rho, p rho. Okay, the exercise that you can do if you are not able, just follow what Sonius tells you to do, is to show that you can always write this product as e to the I x prime rho p rho times composed e to the I over 2 lambda mu nu and mu nu, where x prime rho is equal to, if we are looking at infinitesimal transformations, which means lambda mu nu small parameters. These are the usual Lorentz parameters. This will be equal to x rho plus lambda rho sigma x sigma, which is nothing but a rotation in Minkowski. Okay, therefore, also in this case, we find that the composition law of two particular elements of the Poincare group gives rise to another representative coordinated by x prime coordinates, where x prime is related to the original x by, in this case, Lorentz transformation, this way. Okay. You can do an exercise similar to what we have done for P mu, just to see how the mu nu Lorentz generators act on local fields. So how Lorentz, sorry, how do Lorentz transformations are realized on fields. Okay, so what I want to do is to define Lorentz, we define Lorentz transformations of local fields as, you know, I want to write something which is of the same form sorry that I have to keep go up and down, of the same form as the expression that I wrote down to define translations for local fields. Okay, so I will basically write the same thing, replacing these transformations that depend on P mu with the transformations that depend on mu nu, of course. So we define the transform field evaluated at the new transform point as e to the I over 2 lambda mu nu and mu nu 5 of x e to the minus I over 2 lambda mu nu and mu nu. Okay, but at this point, you can exploit what we have done already for translations. So you can write, well, then let me first of all select this as another important piece of information. Okay, now let me work on it a little bit. So phi prime of x prime is what I have there. But now you can replace phi of x here with e to the I x rho p rho, phi of 0, e to the minus I x sigma, no, let me call it still rho p rho, e to the minus I over 2 lambda mu nu m mu nu. Okay. Now, for this product, you can use what I wrote above here. That product is nothing but this composition that can be rewritten in this way, where remember x prime is nothing but a rotation of the original x. Okay, so let me replace the product with this new expression here. So this is nothing but e to the I x prime rho p rho, e to the I over 2 lambda dot m. Let me be more shorter this way. This product here is nothing but the inverse, of course. Therefore, this is eventually equal to e to the I x prime rho p rho, e to the I over 2 lambda dot m phi of 0, e to the minus I over 2 lambda dot m, e to the minus I x prime rho p rho. We are basically getting the end, because now you see this expression does not depend on x. And what I can simply write for this expression is something like e to the minus I over 2 lambda dot sigma, where sigma is some matrix representation of the Lorentz generators, depending on which is the representation phi belongs to. Okay, if phi is a spinor, I know what sigma is. If phi is a vector, I know what sigma is, and so on and so forth, applied to phi of 0. But this is just a matrix. This is no longer an operator. So it commutes with the rest of the operators. So you can bring this matrix outside, and what you are left is nothing but e to the I x prime p, phi of 0, e to the minus I x prime p, which is phi of x prime. But remember, x prime is the rotated coordinate. So this is also equal to e to the minus I over 2 lambda dot sigma phi of x plus lambda x. Let me write things shortly this way. Okay, so in the case of rotations, you have, as you know very well, you have a double effect when you compute how and you evaluate how your field changes under rotation. You will have a change in the functional form this is nothing but a change in the functional form of the field, because I can call it phi prime, due to the nature, I mean, the representation phi belongs to, but the new phi prime is evaluated in the rotated basis, okay? So this is in fact what we call phi prime of x prime. Okay, I hope this is kind of clear, and maybe this is for some of you just a review of something that you know already, maybe organized in a little bit different way. The main points that I highlighted in red now are there to be and ready to be implemented in a more general setup, which leads us to construct what we call n=1 superspace. Okay, so I will redo basically everything, but considering that now my starting group is no longer Poincaré, is a supergroup that this is what we call super Poincaré. Okay, so now we want to generalize the previous construction to the super Poincaré group. Okay, remember, super Poincaré group is the group whose generators are given by translation generators, rotation, so mu nu, Lorentz generators, and Q bar, the supersymmetry generators. Okay, so basically, remember, we claim that Minkowski space-time is nothing but the coset Poincaré coset Lorentz. I will define superspace to be the coset super Poincaré Lorentz. Okay, so this is definition. N=1 superspace is the super coset given by super Poincaré mod Lorentz, which in a more formal way is OSP for 1 mod SO13. Okay, this is definition. Now let's try to figure out what we can, how we can specify the definition, how we can work in a more detailed way the construction of this superspace. Okay, so as I said, super Poincaré is generated by translations as Poincaré, but also by Q and Q bar. So this time, of course, super coset is again defined as the set of the group of equivalence classes where two elements of the group are equivalent if they differ by a Lorentz transformation. So the definition is the same, but this time we parameterize. So this time we select equivalence class representatives of the form, let me call it L, X, theta, and theta bar, which is still, you know, for the bosonic part, it's still something e to the I, X mu, P mu, fine. This is what we had already in Minkowski. But now remember, I have to take into account that we have extra generators. In particular, these are spinorial generators, Q alpha and Q bar alpha dot. So what I write here is something like theta alpha, Q alpha, plus theta bar alpha dot, Q bar alpha dot. Okay. Therefore, we have introduced, we have more parameters now. We have introduced a set of 4 plus 4 parameters. We have 4 bosonic parameters, x mu, with mu equal to 0, 1, 2, 3, as usual, but plus 4 spinorial parameters, which are theta alpha and theta bar alpha dot, with alpha equal to 1 and 2, and alpha dot equal to 1 dot, 2 dot. Okay, let's stop for a moment here, looking at these new parameters, theta and theta bar. Of course, they are spinorial parameters, so they are anti-commuting objects. Remember that since Q alpha and Q bar alpha dot build up a Majorana fermion, Majorana spinor, then also, of course, theta alpha and theta bar alpha dot is a Majorana spinor, in the sense that theta bar alpha dot is nothing but, remember, according to our conventions, that is a sign, but we don't care, minus theta alpha complex conjugate. Okay. We claim that superspace is then a supermanifold parametrized by the usual, let me call usual, bosonic coordinates, x mu, okay, plus mu spinorial coordinates, which are this theta alpha and theta bar alpha dot. Okay. Let's start trying to get used to these new coordinates. Maybe we can already make a few simple comments. For instance, you might wonder which is the dimension of this coordinate. Remember that when I discuss about dimensions, I always mean mass dimension. Okay, you know that the dimension of x mu is -1 for any coordinate. Let's find out which is the dimension of theta and theta bar. Okay, so let's go back looking at the algebra, which is this one. The dimension of P alpha alpha dot is nothing but, you know, the four momentum vector. Therefore, the dimension of P is 1. It means that, you know, since this has to be true, whatever is the value, explicit value of P, Q, and Q bar, and P, the dimension of Q alpha and Q bar alpha dot is equal to 1/2. So you have 1/2 equal to 1, fine. But therefore, what we obtain, let's go back to the way we write this representative. Of course, the exponent has to be dimensionless, otherwise it doesn't make any sense to have an exponential of something which is dimensionful. If I require the exponent to be dimensionless, and now we learn that Q and Q bar have dimension 1/2, it means that theta and theta bar have dimension -1/2. Okay, so from here we will conclude that the dimension of theta is -1/2 and the dimension of theta bar is -1/2. Okay, great. So this is the first thing that we learn about theta bar, remember, they always have a dimension which is half the dimension of Fs. Okay. At this point, if we pick up for each class a representative of this form, any other element, group element, of the x theta bar class has the form G of x theta bar equal to the representative composed with a Lorentz transformation. This is by definition. Okay. And moreover, we have that we can easily generalize the composition law, the group composition law. Is now generalized to, so if you compose G of x theta bar with another G of another class, let me call it psi epsilon and epsilon bar, this will be another G x prime theta bar prime compose the one possible Lorentz transformation. This is the way we generalize the composition law in terms of representatives and in terms of, you know, these coordinates, the new coordinates x theta and theta bar, which we identify with the coordinates of points in the supermanifold that we call superspace. Okay, maybe we can keep going a little bit more. So, yeah, this is very interesting to do now. Let's remind us what we did. Remember, once we identified in the ordinary case the way we write the representative, and which is the composition law, I told you, let's study two relevant examples, which are these composition laws for which eventually lead to translations and rotations. I will redo basically the same, but now in superspace. So taking for G elements of the supercoset. Okay. So the first relevant example I consider here, remember, in the bosonic case, was the composition of two representatives. Let's see what happens now if I do the same, which means the composition of two representatives when we are dealing with the supercoset. Okay. So we reconsider the two relevant examples of compositions studied above. But now, of course, translated to the language of the supercoset. So the first relevant example was, remember, the composition of a representative, let me call now Lx theta bar, with another representative psi epsilon and epsilon bar. Okay, so this is by definition e to the I x, let me x mu p mu, if you don't mind, I will write x dot p plus theta alpha q alpha plus theta bar alpha dot q bar alpha dot, composed with e to the I psi dot p plus epsilon beta q beta plus epsilon bar beta dot q bar beta dot. Remember that in the previous case, forget about theta and epsilon, this composition was very easy because P commutes with P, and therefore that was simply e to the I, the sum of the two exponents. Now, this is no longer possible. Why? Because P, Q, and Q bar do no longer commute. In fact, remember that Q and Q bar do not commute, and in fact do not anti-commute, and in fact Q bar gives you P. The only thing that you can rely on is the fact that P with Q is 0, so P and Q commute, and P and Q bar commute, okay? Therefore, what I have to do in order to, what do you do usually when you have the product of two exponentials where at the exponent you do have operators which do not commute? You use the famous Baker, Campbell, or Hausdorff formula. Okay, so the composition to perform the composition, use the Baker, Campbell, Hausdorff formula, which, however, in this case, I will tell you in a moment why, goes back to have a simpler expression compared to the most general case. In this case, I can use the fact that if I have e to the A times e to the B, where A and B are two non-commuting operators, this is equal to e to the A plus B plus 1/2 the commutator or the anti-commutator, depending whether these are anti-commuting or commuting objects, period, if every time we have that A commutes or anti-commute with the commutator of A and B does the same. Okay, if this is the case, you can look at the general expression for the Becken-Campbell-Hausdorff formula, and you immediately realize that if this is the case, you know, basically the infinite sum that you would have in the exponent on the right-hand side stops after one step, okay? And this is therefore kind of easier object that we can use. Good, so here what I should do would be to identify A and B with P, Q, and Q bar. So the only thing that you have to do is to realize whether these conditions that I wrote here, which allowed me to simplify the Becker-Campbell-Hausdorff formula, are indeed realized and by choosing for A and B, P and Q bar. Okay. I can tell you in words, this is kind of easy because, you know, to begin with, the only non-trivial anti-commutators that we have is Q with Q bar. So let's take for A here, Q, and for B here, Q bar. Okay, but we know that Q bar gives you P. And when you commute P again with Q, you get 0, in fact. And the same thing when you do it with Q bar. So therefore, this is certainly the case for us. Therefore, we can rewrite this product of two exponentials in a very simple way. So using this observation, basically, what we find for Lx theta bar compose L psi epsilon bar is the following. You get a single exponential. Let me see if I can write it as an exponential. It's a little bit complicated. This is now a single exponential e to the I times what? You will have x. Now let me write everything in terms of alpha dot double spinorial index plus epsilon alpha. Yes, theta bar alpha dot plus epsilon bar alpha dot theta alpha. There is an I here. You have to check. you do the calculation and you will check my expression, plus theta plus epsilon alpha q alpha plus theta bar plus epsilon bar alpha dot q bar alpha dot. Okay, so this is nothing but what we would call L of x prime, theta bar prime, compose a possible Lorentz transformation with what we have found here is that x prime alpha alpha dot is nothing but this long expression alpha alpha dot plus I epsilon alpha theta bar alpha dot plus I epsilon bar alpha dot theta alpha. Theta prime alpha is very simple. Instead, is simply what we call a super translation, because it is a translation in the spinorial coordinates. And of course, theta bar prime alpha dot is equal to theta bar alpha dot plus epsilon bar alpha dot. Okay, so whenever I compose two representatives, which corresponds basically to two different points in superspace, what I get is a new representative which corresponds to having performed a transformation on the x theta theta bar coordinates of my superspace, which are basically given by this expression. And this expression, this kind of transformation is, as I said, what we call a super translation in superspace. The super translation in superspace is generated by spinorial epsilon epsilon bar objects, which realize a very simple usual translation on the spinorial coordinates. It is furthermore parameterized by another psi, let's say bosonic psi alpha alpha dot parameter, which realizes the usual bosonic translation on the x coordinates. But what is important, the bosonic coordinates gets an extra contribution in the translation, still related to the epsilon and epsilon bar parameters. Okay. So this is what we call super translation in superspace. Okay. Let's just go quickly through the second relevant example, rotations. I will not give you any detail here. You will do it as an exercise or just look at Sonius. But in any case, even if you look at Sonius, you have to do some calculation. So in the second relevant case, remember, we take a G to be a Lorentz generator. This is still what we take even in this case. Okay. And what you will find, if you do the calculation, is that if you now recompose this G with a representative, yeah, this is equal to L of x prime, theta bar prime, composed e to the I over 2 lambda dot m, where now x prime alpha alpha dot is equal to x alpha alpha dot minus x beta beta dot lambda beta beta dot alpha alpha dot. This is the usual x rotation. Okay. Then you will do the calculation. If you do it and you get the right answer, you have done already a good job in superspace. This is equal to theta beta of e to the minus I over 4 lambda dot m. Sorry, lambda, well, I should write it lambda mu sigma mu. These are our sigma mu that we introduced at the very beginning of the course, 2x2 matrices, beta alpha, and theta bar prime alpha dot is equal to e to the I over 4 lambda mu nu sigma mu nu alpha dot sigma bar alpha dot beta dot theta bar beta dot. And but these are nothing but what I do expect Lorentz transformation acting on theta and theta bar, because remember theta and theta bar are the Weyl components of a Majorana spinor, therefore they rotate under Lorentz transformations according to the usual rotational rules, okay? And this is, okay, what we can call the rotations in superspace. Okay, I think, you know, if you go through what we have done for the bosonic case, the last thing that we should do is to see how we should realize, how we realize the action of the generators, the super Poincare generators that now are P, Q, and Q bar on local fields. So first of all, I have to define a generalization of local field when we refer to superspace. So we will define a local superfield in superspace. And then I want to see how P, Q, and Q bar acts explicitly on local superfields. Remember, in the ordinary case, we found that P mu is nothing but minus the derivative respect to mu, to x mu. We want to see what Q and Q bar are. Okay, but this requires a bit of attention, so I think we might stop here for a little break. Okay, so yeah, you hear me and you see my screen, yes, okay. Let's keep going. Now, forget about rotations. Let's go back to super translations. Now, what I want to do, we want to generalize the definition of local field to superspace. Okay. Okay, so the first obvious thing that you can do is to generalize, you know, in the ordinary Minkowski space, what we consider is a set of smooth functions of x. Okay, we will now consider the set of smooth functions of x, theta, theta bar. Okay, this is something that I can always do. And we require, again, a locality principle or constraints. I don't know how you want to call it. In superspace, as we did before for the ordinary Minkowski spacetime, we define a local field, a field that in terms of variables x prime, theta prime, and theta bar prime has a functional expression, phi prime, such that this is exactly equal to phi in coordinates x, theta, theta bar. This is what we impose as a constraint, as a local principle. Okay. And in particular, if we now look at the sorry, I have to keep going up and down. If we now look at the super translations, we can write, let me give you this name. We can write this as x alpha alpha dot plus delta x. Okay, so all the expression that we obtain here is what we call delta x. And remember, for theta and theta bar, we have the usual simple translation. Therefore, super translation that we consider is x prime equal to x plus delta x, theta prime equal to theta plus epsilon, and blah, blah. Okay, so let's focus on super translations. Oops. So for super translations, what we have here as x prime, theta prime, and theta bar prime will be x plus delta x, theta plus epsilon, theta bar plus epsilon bar. Okay, therefore the locality constraint can be simply written as phi prime of x plus delta x, theta plus epsilon, theta bar plus epsilon bar has to be equal to phi of x theta theta bar, or as we did earlier, equivalently, phi prime of x theta and theta bar equal to phi of x minus delta x theta minus epsilon theta bar minus epsilon bar. Okay, so basically what I have been doing since the beginning of the lecture on the bosonic coordinates, now we replicate it also on the fermionic ones. Okay, if we consider, as we did earlier, if we consider infinitesimal transformations, so for infinitesimal translations, which means, remember, psi, epsilon, and epsilon small, epsilon are very small. Okay, we can expand, in fact, this expression in powers of delta x, epsilon, epsilon bar, stopping the expansion at the first order in these parameters. So we can write that phi prime x theta and theta bar. Okay, now let's do two things in one shot. As we did before, if I want to compute the functional variation, which is by definition phi prime of x theta theta bar minus phi of x theta theta bar. Okay, this is looking at the previous expression, phi of x minus delta x, theta minus epsilon, theta bar minus epsilon bar, minus phi of x theta theta bar. Okay, now you expand this at the first order, and you will end up with the minus delta x alpha alpha dot d alpha alpha dot phi minus epsilon alpha derivative respect to theta alpha of phi minus epsilon bar alpha dot derivative respect to theta bar alpha dot of phi. Okay. Okay, therefore, we meet new kind of objects. So we have new kind of derivatives that are the spinorial derivatives. Okay, let me call them d alpha. By definition, this is the derivative respect to theta alpha, and d bar alpha dot. By definition, this is the derivative respect to theta bar alpha dot. Exactly the objects that I find here when I expand. And they are, well, this is convention. Our conventions are the following. If you apply d alpha to theta beta, my convention is that this is minus delta alpha beta. And if you apply d bar alpha dot to theta bar beta dot, this is delta alpha dot beta dot. But you can even find different conventions. It's just to decide once forever, which is our definition of derivative. Very good. Therefore, okay, this is it. So what we have found is that the functional variation of my object that I didn't define actually, this smooth functions from now on is what I would call a superfield. Okay, these are fields, the ones that are defined in ordinary Minkowski. The generalization to superspace is called superfield. Okay, so the functional variation of my superfield is, in fact, as we wrote up, the delta x d alpha alpha dot phi minus epsilon alpha d alpha phi minus epsilon bar alpha dot d bar alpha dot phi. Good. Okay, however, this is, keep it there. Let me call this 10. Okay, however, we would like to generalize identity. Sorry, I have to go up now because this was done at the very beginning. Okay, this identity 4, which is the definition of how you define the translated field in terms of the action of generators P mu to the case of superspace and superfields. So we want to generalize identity 4 to superfields. Okay. And, you know, in the ordinary case, we wrote that phi, sorry, no, this is, let me check which kind of conventions I was using. Sorry, where is it? Here, okay. Let me consider 4 written in this way. I better try to generalize this expression with L and being the representative of the coset, okay? So we write now that, so this is something that you know already, okay? Phi prime of x theta theta bar is equal to, without prime probably, let's put in this way, equal to L x theta theta bar phi of 0, 0, 0, L inverse of x theta theta bar. This is a generalization that we wrote there, or more generally, phi of x prime theta bar prime equal to L of psi epsilon epsilon bar phi of x theta theta bar L inverse psi epsilon epsilon bar, where as usual x prime is equal to x plus psi plus epsilon theta plus epsilon bar theta bar, and then where I maybe here theta prime is equal to theta plus epsilon and theta bar prime equal to theta bar plus epsilon bar. Okay. Okay. Therefore, I can use this new identity, maybe 11, to compute the functional variation delta phi 0 in an alternative way. We did compute already it in this way in terms of derivatives, but I can compute this in an alternative way, which is using this new identity that I wrote here. Okay, so we can compute delta 0 phi alternatively as, so delta 0 phi by definition is phi of x prime, it was phi prime of x theta theta bar minus phi of x theta theta bar. Okay, but that was phi of x minus delta x, theta minus epsilon, theta bar minus epsilon bar, minus phi of x, theta theta bar. And now what you do is to express this first term using identity 11, using the way we define the action of PQ and Q bar on the fields. Okay, if you now use identity 11, this is L inverse of psi epsilon epsilon bar applied to phi x theta theta bar, L of psi epsilon epsilon bar minus phi x theta theta bar. Okay, note that here when I write the general identity, I have L and L inverse. Here I have the opposite, L inverse L, because now I'm doing a backward translation with minus delta, minus epsilon bar. Okay, now what you can do is to expand, you know what this expression is. This is e to the minus I psi dot p plus epsilon alpha q alpha plus epsilon bar alpha dot q bar alpha dot phi x theta theta bar e to the I x dot p plus epsilon q plus epsilon bar q bar minus phi of x theta theta bar. What you do now is simply expand these exponentials at the first order in psi epsilon epsilon bar. Remember, we are doing infinitesimal translations. Of course, as it happened already in, sorry, this is psi. As it happened already in the bosonic case, when you expand, for instance, the linear term in psi is proportional to B commutator with phi. Now, what happens is, of course, that the linear term is in epsilon will be proportional to Q commutator with phi and blah, blah, blah. So eventually this is nothing but minus I psi alpha phi dot, P alpha phi dot commutator with phi, minus I epsilon alpha commutator of Q alpha with phi, minus I epsilon bar alpha dot commutator of Q bar alpha dot phi. Okay, great. Let me call this 12. Done, because now, remember, I told you we computed already this variation and we got this expression. Okay, now alternatively, we compute the same thing and we got this expression. So you have to compare and identify results 10 and 12. We eventually find that P alpha phi dot commutator with phi. Fortunately, this is exactly what we found already in the bosonic case, because, you know, a good check of what you have been doing is that whenever you set theta, theta bar, epsilon, epsilon bar equal to 0, you have to go back to what you did already in Minkowski. Okay, so this is good. But now you have new results. You learn now how the generators of supersymmetry act on superfields. And what you find in the comparison is that this is equal to d alpha plus I theta bar alpha dot d alpha alpha dot applied to phi. And similarly, q bar alpha dot applied to phi is equal to minus I d bar alpha dot minus I theta alpha d alpha alpha dot applied to phi. This is another very important piece of information, okay? So to wrap up what we have done so far, we have defined, forget about details and the geometric construction, we have generalized Minkowski to a sort of super Minkowski, let me call it super Minkowski. This is not really super Minkowski, a superspace where the local objects are defined in terms of smooth functions of x, theta, and theta bar, which are the coordinates of the superspace. These local functions are called superfields and imposing locality and, you know, defining in a suitable way the translation of this superfield, we do find how the generators of a super Poincare, P, Q, and Q bar act on the on superfields. Okay. Of course, superfields can also carry some non-trivial Lorentzian index, which means that they can be non-trivial representations of Lorentz transformation. So together with this table of definitions, you will also have the usual definition of the action of M mu nu on your superfield, which will be given by the famous matrix, Lorentz matrices that we introduce, depending on which kind of representation is realized by your superfield phi, you will have different matrices. Okay. Okay. Fantastic. So the important, if you wish, check that you may do is the following. So this is an explicit realization of super Poincare generators acting on superfields. What you can check easily is now the following. This is an important consistency check. If you now compute the anti-commutator of QQ bar acting on phi, and you use this explicit realization, so this will be d alpha plus I theta bar alpha dot d alpha alpha dot, anti-commutator with d bar alpha dot minus I theta alpha d alpha alpha dot. I have too many, sorry, I should change. Indices here, plus I theta beta, bar beta dot, alpha beta dot, and this is minus I theta beta, d alpha beta alpha dot. Okay, should be correct. If you perform explicitly this anti-commutator, okay, you will find that this is equal to minus 2 I d alpha alpha dot, but this is nothing but 2p alpha alpha dot applied to phi. Okay, according to our identification here. Therefore, a consistency check of what you have done is that, you know, the explicit realization of PQ and Q bar, in fact, satisfies the correct algebra of anti-commutator. Remember that Q bar has to give you 2p. Okay. Good. So in conclusion, the conclusion is that in terms of super translations of superfields are given by, we have a bosonic super translation parameterized by psi, which is I psi alpha alpha dot P alpha alpha dot applied to phi. And in fact, this is minus the derivative of phi. Then we have an epsilon translation, which is I epsilon alpha Q alpha applied to phi. And finally, another super translation parameterized by epsilon bar, which is I epsilon bar alpha dot Q bar alpha dot phi, where, remember, now P, Q, and Q bar act on phi in this explicit way. Okay, these are the super translations that we can define in Superspace. Okay, in particular, as you can immediately realize, this kind of super translation, the super translation, let me do it this way. Okay, this kind of super translations, the ones parameterized by epsilon and epsilon bar, are nothing but what we have identified so far as the supersymmetry transformation, this time realized on superfields. Okay, because remember, supersymmetry transformations are generated by the action of the generators Q and Q bar on your objects. My object right now is a superfield. Okay, so this is nothing but supersymmetry transformations. So these are SUSY transformations on superfields. Okay, therefore, what I have realized, and I hope you get this point, in the language of superspace, in terms of superfields, supersymmetry transformations are nothing but super translations, because remember, epsilon in terms of superspace coordinates, epsilon and epsilon bar parameterize super translations. Okay, therefore, this is important. In superspace, SUSY transformations are realized as super translations. Maybe I should write it as super translations. SUSY transformations are super translations. Okay, exactly as in Minkowski, you know, coordinate translations give you the usual transformation of fields. Okay, yeah, we still have some time. Maybe I can stop here if you have questions for 1 second. I don't see any question. Good. So let's go on now with the algebraic construction. You know, now let's put in this way. Whenever you have a space, when we talk about, you know, space or space and Minkowski space time, whatever, what you would like to do once you have defined smooth functions on this space, you would like to basically build up all the differential calculus and integral calculus on this space. Okay, now we have a superspace where my main objects are super fields. I want to build up differential calculus and integral calculus in superspace. Okay, so let's put differential. Let's start with differential calculus, and then we will do integral. Sorry. differential calculus in Superspace. Okay, so in Superspace, remember, is so points, Superspace points are coordinated by x mu, theta alpha, theta bar alpha dot coordinates. Okay, we have already introduced the usual derivatives. Derivatives are d alpha alpha dot. Let me stick to the double index notation. So let me write the x mu as x alpha alpha dot. So we have the usual d alpha alpha dot, which is the derivative respect to x alpha alpha dot. Then remember, we introduced d alpha, which is the derivative respect to theta alpha, and d bar alpha dot, which is by definition the derivative respect to theta bar alpha dot. Okay. The question is, are we happy with these derivatives? In which sense we should be happy? In the following sense. In ordinary space, where we only have d alpha alpha dot, the derivative respect to x, okay, what happens is that if you consider the transformation under translations of the derivative of a field, this is equal to the derivative of the transformed field. So translations commute, or put in the opposite way, derivative, the ordinary derivative commutes with the transformations. Why? Because translation transformations on fields are nothing but derivatives, and then, you know, ordinary derivatives commute. Leibniz rule. Okay. When this kind of behavior is realized, and this is what I'd like to have realized, we say that the derivative is covariant with respect to translations. Okay. The alpha alpha dot is covariant derivative. Now we have introduced two other derivatives, this the alpha and the bar alpha dot. I'm wondering whether these derivatives are covariant. This time, of course, with respect to the translation, they are. But now I have to put into the game also SUSY transformations, the ones generated by Q and Q bar. Maybe we may call this delta P, generated by the generator P. Okay. So we wonder whether, when I consider d alpha phi, now this is a super field, d alpha phi, and I take a transformation delta P, I'm wondering whether this is the d alpha of delta P of phi. What do you think? Since remember, this is related to with respect to the spinorial coordinate. This is something acting on the bosonic coordinates. I would say yes, this is for sure true. But if I consider delta Q of d alpha phi, this is no longer true, and I will show you why. Okay. In fact, let's consider that, if I want to build up delta Q of d alpha phi, I have to act with Q, let's consider Q bar. q bar alpha dot d alpha phi. Okay. On the other hand, when I consider d alpha of delta q bar phi, this is d alpha of q bar alpha dot phi. Okay. The fact that the two equations, the two expressions do not coincide comes from the end. The fact that d alpha does not commute with q bar alpha dot. You know, basically what I'm asking here is whether acting first with the alpha and then with q bar is the same that as acting first with q bar and then with the alpha. So I'm basically wondering whether the alpha anti-commute with q bar. And the answer is no. In fact, if you compute this anti-commutator, remember that q bar alpha dot is minus I, d bar alpha dot minus I theta beta, d beta alpha dot. Okay, what happens when you do this calculation? These two derivatives anti-commute, fine. But when d alpha acts on theta beta here, you get something which is proportional to d alpha alpha dot, which is not zero. Okay, therefore, d alpha, the same thing holds for d bar alpha dot when you try to anti-commute with q alpha, are not covariant derivatives for SUSY transformations. Okay. But this is not a big deal because we, starting from these small derivatives, we can build up covariant derivatives. Okay, we then prefer to construct SUSY covariant derivatives, which are defined this way. Rather than talking and using small d alpha, I will use a big d alpha, which is covariant, which is by definition the small one minus I theta bar alpha dot d alpha alpha dot. And the same for alpha dot. I'll just take the complex conjugate. Okay, you can easily check. You can easily check that if you anti-commute the alpha with the q bar alpha, q bar, let me call it beta dot, and the alpha with the q beta, you will get 0, and the same for d bar. Just check it. Okay, therefore, we can claim that if I perform a SUSY transformation of d alpha phi, this is the same as applying the derivative after acting with the SUSY transformation. So these derivatives are my best, my preferred derivatives, of course, when I want to build up the differential calculus in Superspace. So we never work with the small derivatives. We will always work with these big derivatives, big D derivatives. Moreover, two nice, not I mean, even three nice observations, important observations. The first one is that this is also something that you can easily check. If you consider anti-commuting two derivatives, d and d bar, you will get 2p alpha alpha dot. So D and D bar as Q and Q bar, they satisfy the same algebra. And of course, D alpha, D beta is equal to 0, and D bar alpha dot, D bar beta dot is equal to 0. Same algebra of Q bar. First observation. Second observation, this will be useful maybe tomorrow. Now we are more or less approaching the end. You can see from the definition of D that D can be written as I Q alpha minus 2I theta bar alpha dot D alpha alpha dot. And similarly, D bar alpha dot is I Q bar alpha dot plus 2I theta alpha D alpha alpha dot. Okay, so what I want to stress for the time being, probably for you doesn't mean anything, but keep it in mind. What I want to stress is that D and Q, and similarly D bar and Q bar, differ by terms which are proportional to theta and theta bar. Okay, this will be important because basically whenever, as we will see tomorrow, whenever you have to set theta and theta bar equal to 0, D and Q and D bar and Q bar become basically the same object. So just for future record, keep it in mind. The third observation is instead a little bit deeper. This concerns the geometry of superspace. Okay. So let me first of all remind you that in curve space, what we usually have is, of course, the definition of covariant derivatives. Both in curve space, when we talk about curve space-time, or even in gauge theories, remember. And covariant derivative satisfy a very general algebra. So the algebra of covariant derivatives is the following. If you commute or anti-commute, well, in ordinary space, you commute, of course, two covariant derivatives. This is equal to, I mean, these are kind of geometric object that you build up in your space. Okay. And when you have this general identity, you call this the torsion of your space, and this the curvature. Okay, of course, this can be generalized to superspace in terms of superspace derivatives. Now we have, so let's generalize to superspace, where now the covariant derivatives are let me call them dA with a big A. They are, by definition, d alpha, the covariant derivative d alpha that I have just introduced, the corresponding d bar alpha dot, which is basically the complex conjugate, and the ordinary space-time derivative. Okay, so for me, this big A has is a parameter which takes values as alpha, alpha dot, and alpha, alpha dot. Hope it is clear. Okay, therefore, I can generalize the previous algebra in something similar. Now the algebra becomes dA dB, where now this will be commutators or anti-commutators, depending whether you are dealing with the spinorial derivatives or the space-time derivative. In any case, you can define this to be TABC DC plus RAB. Okay. Okay, now you simply plug these derivatives here. So you specify your algebra for A and B equal to alpha, alpha dot, beta, beta dot, or alpha, alpha dot, beta, beta dot. Okay, you rely on the covariant derivative algebra that we have just discussed here. I told you that basically the covariant derivatives, the spinorial covariant derivatives satisfy the same algebra of Q and Q bar. In addition, you have that the usual space-time derivative, d alpha alpha dot, commutes with the alpha and with the bar alpha dot. Of course, it commutes. If you look at the explicit definition of these objects, there is nothing that does not commute with the ordinary space-time derivative. Okay, they commute. Okay, you take into account all this information. So from previous construction, we find that first of all, R is always equal to 0. You do not have any terms of this form, whereas for T, A, B, C, the only non-vanishing object is T alpha. Let me call it beta dot, and C expressed in terms of the double spinor notation, gamma gamma dot, and this is minus 2I delta alpha gamma delta beta dot gamma dot. This is something that you should do as an exercise because this is very instructive. Okay, so conclusion is that superspace, at least the rigid superspace that we have constructed, is flat, no curvature, with torsion. There is a non-trivial torsion. Okay, therefore, n equal 1 superspace is a flat manifold with torsion. And this is an interesting property of superspace. Okay. Okay, this is the differential calculus. Basically, I introduced, all possible derivative, and I mean, a consistent set of derivatives. Tomorrow we will go through the integral calculus, but before doing that, let me simply mention something now, and we will elaborate more on it tomorrow. Let's consider the most general superfield. As I said, this is a smooth function of x, theta, and theta bar. However, theta and theta bar are spinorial objects. Therefore, if you consider theta cube, this is equal to 0, of course, and theta bar cube is equal to 0. Okay, because they are spinorial objects, And in particular for theta, for instance, the only components are theta 1 and theta 2 for alpha equal to 1 and 2. Okay, so if you take theta 1 square is 0, because this is spinorial, and theta 2 square is 0 as well. Therefore, you can build up theta square defined as theta 1, theta 2, but stop. You cannot multiply by an extra theta. So theta cube and theta bar cube are 0. Okay, therefore, this phi is by definition a smooth function of x theta and theta bar. You can think of expanding phi in Taylor expansion in theta and theta bar. But the Taylor expansion will not be an infinite series now, because, you know, at the third order, you stop. Okay, so Taylor expanding in theta, theta bar, you can write this in the following way. You will have a first, let's say, a 0 order in theta, which is simply a function of x, plus a first order in theta times chi, which will be a spinor, function of x, and similarly for the theta bar. Okay, then we can have second order expansion plus theta bar square. Well, let's write for the time being n. Okay. As a second order term, you can also have theta alpha, theta bar alpha dot. Therefore, here you will have a alpha alpha dot x, which is nothing but a vector. Then you can have theta bar square, theta alpha times some lambda alpha of x. You can have theta square, theta bar alpha dot times some lambda bar alpha dot. Let me put in the opposite direction. Alpha dot, lambda bar, alpha dot x. And finally, as the last term, you can have theta square, theta bar square times, again, a scalar, but no more than that. The expansion stops here. Okay, so the nice thing that we will use tomorrow is that for any smooth function of the superspace, which is what we call superfield, you can have a finite expansion in theta. And what we will argue tomorrow is that the components of the expansion, so C, chi, chi bar, n, and so on and so forth, are nothing but the components of a supermultiplet. So they realize a representation of superalgebra. So this just to close the loop. I told you at the very beginning of the lecture that superspace is a very convenient and compact way to represent, to realize the representations of superalgebra. And in fact, this is why, because in the expansion of a superfield, you have all the components of a supermultiplet. But we will discuss about it further tomorrow. I think this is time to stop for today.